In our last lecture, we introduced this phenomenon known as electromagnetic induction, that when the magnetic flux through a circuit changes in time, an EMF and current are induced in the circuit. Faraday's law tells us specifically how the induced EMF relates to the rate at which the magnetic flux through the circuit changes in time. In today's lecture, we'll start by taking a look at the significance of that minus sign in Faraday's law, known more commonly as Lenz's law, and see how this will ensure that energy is conserved in our circuit. We'll look at some applications of Lenz's law, and finally, we'll end today's lecture by exploring a generalized form of Faraday's law that applies even when a physical conducting circuit does not exist.
So we know that a current gets induced in a circuit when the magnetic flux through it changes in time. But how do we know the direction of the induced current? That's what Lenz's law, that's where it comes into play. Lenz's law, named after the physicist Emil Lenz, pronounced Lenz, not Lenz, who formulated it in 1834. This law addresses the negative sign in Faraday's law and allows you to predict, the direction of the induced current. We'll start by giving a statement of it. Don't be intimidated. It's going to sound confusing at first exposure. But after stating it, we'll talk about a step-by-step procedure that will allow you to apply it. So here's a statement of Lenz's law. It tells us that the direction of the induced EMF and current is such that the magnetic field created by the induced current opposes the change in magnetic flux. That is certainly a mouthful, and look, what I care about is that you know how to apply this in solving problems. So you could apply it to be able to determine the direction of the induced current. I'm not going to ask you to give a statement of the law. So let's not waste any more time. Let's talk about how can you use Lenz's law, how can you apply it in order to predict the direction of the induced EMF and induced current. I'm going to outline a three-step process here, for doing this. Yes, it takes 3 steps, just to determine the direction of an induced current. So in the first step, we're asked to identify the change in the magnetic flux caused by the action. In any problem, some action is going to be taken, whether it's sticking a magnet into a coil, whether it's flipping a switch that's going to create a magnetic field. There's going to be some action in the problem that is going to cause the magnetic flux through your circuit to change in time. You need to see whether the magnetic flux increases or decreases as a result of this action. Once you've done that, the second step then is to identify the direction of the induced magnetic field that would be caused by the induced current needed to oppose the change in magnetic flux. So there's 2 possibilities here. When the magnetic flux decreases, that tells us that the direction of the induced magnetic field must be in the same direction as the original magnetic field in order to oppose the change in magnetic flux. Likewise, when the magnetic flux through your circuit increases in time, the direction of the induced magnetic field must be in the opposite direction of the original magnetic field. Why? In order to oppose the change in magnetic flux. So you can see here that in a lot of ways, Lenz's law is like other laws we see, in the physical world, where an equilibrium or status quo is trying to be maintained by our system. So in a sense, we can say that when a change is made to the system, the system will respond by creating an induced EMF and current and magnetic field, that will try to counteract the change. So once you've determined okay, the direction of the induced magnetic field, okay, the third and final step is to identify the direction of the induced current that would be required to create such an induced magnetic field. Okay, and of course to do this, you're going to have to use your right hand rule, okay, where you will let your fingers of your right hand, okay, point or curl in the direction of the induced magnetic field so that your thumb will point in the direction of the induced current. Now, I'm going to be honest here. Okay, it is important that you follow this procedure when you apply Lenz's law. Okay, history tells me that Physics 103 students, okay, especially those of the millennial generation, are always trying to look for shortcuts. And I know, okay, for some of you, 3 steps is just too much, okay, to expect you to do. And that's where everything is going to go wrong. Okay, just saying. All right, so it is now time to apply this 3-step procedure, okay, and applying Lenz's law to some problems. So we'll see here in our first problem, okay, we're told that the north pole of a magnet moves towards a solenoid. Notice that in the columns here, these 3 columns, each column represents one of the steps in the process, okay, that we need to figure out, okay, in order to find the direction of the induced current. So, okay, you'll see here that the direction of the original magnetic field, I'll call B naught, okay, is in the direction of these magnetic field lines. And you can see that when we move this magnet, the north pole of this magnet, towards the coil, okay, what's going to happen to the magnetic flux through the coil? Well, as we move it towards the coil, more magnetic field lines will penetrate the coil, okay, which means that the flux through the coil, the solenoid, will increase. Given that, we now know that the direction of the induced magnetic field, okay, must oppose the change in flux, okay, according to Lenz's law. So since the magnetic flux increases, okay, how will the system respond by trying to oppose that flux change? Okay, it's going to respond by inducing a magnetic field that's opposite in direction to the original field. Okay, and once we know that, once we know the direction of the induced magnetic field, okay, we can now use our right hand rule to determine the direction of the induced current. Okay, so here, when you take your right hand here, okay, remember that you're going to take your right hand, you're going to place the fingers of your right hand in the direction of the induced magnetic field, okay, and on the interior of that circuit, when we do that, that means our thumb is going to point in the direction of the induced current. And when you are looking at that loop from the left-hand side, you will see that the direction of that induced current is counterclockwise. All right, so in the second example, okay, we are told here that okay, the action taken by your fingers here to actually pull this coil apart so that we decrease the area of the coil. So once again, what effect is this going to have on the magnetic flux? Okay, when the surface area decreases, the amount of field penetrating that coil will decrease. That's going to cause a decrease in magnetic flux. So according to Lenz's law, okay, the system will respond by trying to counteract that change. That means that the direction of the induced field will be in the same direction as the original field, okay, in order to counteract the change in magnetic flux. So you can see here that the induced magnetic field then, okay, will be in the same direction as the original magnetic field. To find the direction of the induced current, we're going to take the fingers of our right hand, okay, and in the interior of the loop, we're going to let them point inwards into the plane of the paper or into the plane of your computer here. And you'll notice that your thumb, okay, is going to point in the direction of the induced current. So when you do that for this circuit here, okay, for this coil, you'll see that your thumb is going to be pointing in a clockwise, okay, fashion here. Okay, so the induced current will be clockwise. In our last example here, we're told that we're going to rotate this coil in a uniform magnetic field 1/4 of a turn. So if we start the coil in its position that you see here, okay, you see that the flux through the coil is now a maximum, but by rotating it 1/4 turn, okay, you will see then that the amount of magnetic field penetrating it is going to decrease in time. In other words, the magnetic flux through the coil will decrease with that action. How will the system respond? Okay, according to Lenz's law, the induced magnetic field must be in, okay, the same direction as the original magnetic field to try to counteract that change in magnetic flux. So we now say, what would be the direction of the induced current? Okay, well, the induced current, using our right hand rule, when you place the fingers of your right hand, okay, in the interior of that loop and let them curl inwards, just like in the problem above, you see that your thumb is going to point, okay, in a clockwise direction. So we would say the induced current is clockwise.
Always listen to the hand, folks. Listen to the hand.
In our next example, you see here that we have a circuit consisting of a solenoid, okay, which is placed near this metal ring. And you'll see that before we flip the switch, before the switch is activated, there is no current in our circuit and therefore no magnetic field that penetrates the ring. But once we flip the switch and complete the circuit, okay, a magnetic field will get created in the ring, okay, in the direction shown. And the original magnetic field then, when the switch is flipped, will be to the left. So obviously, okay, the change in flux caused by the action, there is no magnetic flux because there is no field to start out with, but when the switch is flipped, okay, now this magnetic field exists to the left, so clearly the flux through our circuit increases. According to Lenz's law, okay, the system will respond by trying to counteract this increase in magnetic flux. How will it do that? Okay, by inducing a magnetic field, okay, which will be opposite in direction to the original magnetic field. Okay, so the induced magnetic field, by being opposite in direction to the original magnetic field, okay, will oppose this increase in magnetic flux. In order to figure out the direction of the induced current, you now have to use the right-hand rule. So in this case here, you need to stick the fingers of your right hand in the interior of the iron ring in the direction of the induced magnetic field. And when they do that, when you place your fingers of your right hand there, you will see that the direction of the induced current, okay, is going to be clockwise, okay, in the direction of this arrow here I'm showing you on the screen. So in our last example, we return to the case of the motional EMF, where we have these two conducting rails, a resistor on one end, and a metallic bar which is free to slide on the other end, okay, so that we have a complete circuit. And you will see here that this arrangement exists in a uniform magnetic field that is directed inwards into the plane of the paper, into the computer screen that you're looking at. And when the bar slides to the right, if we consider that to be the action, what effect is that going to have on the magnetic flux? Well, clearly it's going to cause the magnetic flux through the circuit to increase as the circuit area increases. So, according to Lenz's law, how will the system respond? okay, the system will respond to this increase in magnetic flux by trying to decrease the magnetic flux, by trying to counteract this change. It will do that by creating an induced magnetic field, okay, I'm showing you here, that is opposite in direction to the original magnetic field. That's how it will counteract this flux increase. And that induced magnetic field then, okay, is set up by this induced current. To figure out the direction of that induced current, we use our right hand rule. And when you take the fingers of your right hand, you stick them in the interior of the loop in the direction of the induced magnetic field, okay, you will see that, okay, your thumb must point, okay, in this counterclockwise direction, telling us that the current induced in the circuit, okay, according to Lenz's law, will be in the counterclockwise direction. So in this slide, we'll take a look at the relationship between Lenz's law and the law of conservation of energy. And we'll see that if Lenz's law was not true, then the conservation of energy principle would be violated. So to see this in the form of a proof, we will do what we've done many times in the past, and that is we will assume the opposite of what we believe to be true and show that by doing so, by assuming the opposite, this leads to an inherent contradiction. So we will start by assuming that the minus sign in Faraday's law did not exist, in which case Faraday's law would look like this. Okay, it would imply that the induced EMF, okay, would give rise to an induced current that produces a flux change that would be in the same direction as the original change. Now you can hopefully see what happens here, that this greater change in flux would produce an even greater induced EMF, okay, and greater induced current, which produces an even greater change in flux, and so on. So this current, this induced current, would grow indefinitely, producing energy even after the original stimulus had ended. So clearly energy, okay, would be created in this process in violation of the law of conservation of energy. And so you see then that the minus sign in Faraday's law must exist if the law of conservation of energy is to hold true.
In this next example, you'll see a nice illustration of Lenz's law in what I call the falling magnet mystery. Just to note, being an observant scientist, I'm guessing you'll recognize that I was just a tad bit younger when the demonstration was videotaped. If truth be told, this demonstration was for a conceptual physics class I was teaching at the time. While we did discuss the concept of electromagnetic induction in that course, we didn't introduce Lenz's law. Okay? Hence, you won't be confused when I say as much during the video clip. Let's take a look.
Right, this is what I call the falling magnet mystery, a great place to see electromagnetic induction in action. Let me explain the apparatus here. What we have is we have two tubes. We have a glass tube and we have an aluminum tube, both of the same length. And what I have in my hands here is I have two objects that have exactly the same mass, but one of these objects happens to be magnetic while the other object is not magnetic. Notice they're identical in size and shape, but they have different magnetic properties. Now, what I want you to notice here is that the magnet, well, certainly your life experiences tell you that a magnet is not attracted to glass in any way. But this aluminum tube, although it is metal, okay, aluminum is a paramagnetic material, is also not attracted to the magnet either. Okay, but what we're going to do is we're going to let these objects fall through these tubes, and we're going to qualitatively measure the fall times and make some observations here. So let me start by taking the non-magnet, and letting it fall through the glass tube, okay, and just qualitatively measure its fall time. Okay, it behaves as a freely falling body, as you'd imagine. And if I do the same thing through the aluminum tube, okay, you'll see that its fall time is virtually the same. Let me now take the magnet and let it fall through the glass tube. Okay, and you see it has virtually the same fall time as the non-magnetic object. But now let me take the magnet and drop it through the aluminum tube. Okay, and let's take a look at what happens to its fall time. You see how great the fall time is. Somehow it is being slowed down during its fall through that aluminum tube, although it has no attraction to aluminum. So to try to explain what's going on here, well, we need to look at the concept of electromagnetic induction. The physics is quite complicated, so we're going to simplify it a little bit. And what I want you to do is imagine that as this magnet falls through the tube, let's consider a little piece of that tube above the magnet. So I have this ring here, which we can imagine is that piece of tube directly above the magnet. Now, you can imagine that as this magnet is falling through the tube, take a look at the magnetic flux through that piece of tube above it. As it falls downwards, the magnetic flux through the ring above it is changing in time, it's decreasing. That change in magnetic flux, according to Faraday's law, induces a current. That induced current creates a magnetic field. Now, there's a concept in physics we haven't discussed called Lenz's law, which says that the direction of that induced magnetic field is opposite in polarity to the magnet, the falling magnet, which created the magnetic field in the first place. The end effect is that the magnetic field created, because it's opposite in polarity, is going to pull up on this falling magnet a little bit, slowing down its motion. We could similarly apply the same physics to a segment of the tube below the falling magnet, and you'll notice that as that magnet falls towards that segment of tube below it, the flux increases. That changing flux induces a current. That induced current creates a magnetic field, which once again is opposite in polarity to the falling magnet, the magnetic field of the falling magnet that created it. And that opposite polarity means that it's going to push up on the magnet a little bit and slow down its motion. So as we can see, this magnet gets slowed down as it falls through the aluminum tube. A great place to see electromagnetic induction in action.
Let's see if we can now explain this apparent mystery. So let's consider this to be the falling magnet, and it really doesn't matter whether you drop the North Pole facing down or not, but okay, you can see with the orientation I'm showing you here, okay, by the direction of the magnetic field, we're assuming the North Pole of the magnet is facing downwards. And in order to see the currents that get induced, we have to remember that this is a solid aluminum tube. It's not as if we have a circular piece of conducting wire to form a circuit. Okay, but you'll notice that any piece of that conducting tube we want to look at, we can think of as a circuit. So what we're going to do is we're going to start by taking a look at this piece I'm showing you in red here, which is above the falling magnet. Let's take a look at the induced current in that region and the induced magnetic field, okay, that it creates. So as the magnet is falling, when we look at the region above the magnet, okay, well, we see here that above the magnet, the magnetic flux is decreasing in time as the magnet is falling away from that region. I'm showing you here the direction of the original magnetic field. So according to Lenz's law, the system is going to respond, that induced current and induced EMF will oppose the change in magnetic flux. That means that the induced magnetic field must be in the same direction as the original magnetic field, okay, to oppose that flux change. So here is the induced magnetic field direction. Now, to better understand this, let's treat that induced magnetic field as if it were a tiny magnet. And what you can see here is that to give a direction of magnetic field like that, this would suggest that, notice the induced magnetic field and the original magnetic field are in the same direction. That means that if we think of that induced magnetic field as being caused by a tiny little magnet in that region, it should be oriented in exactly the same way as the original magnetic field. So the overall effect, you'll notice here, we see that the North Pole here is going to be attracted to the South Pole here, which means that there's going to be the slight upward force on our falling magnet due to that induced magnetic field. The opposite poles attracting each other. Likewise, when we look at the region below the falling magnet, there we can see, and here's the original magnetic field direction. As the magnet falls towards that region, there we can clearly see that the magnetic flux in that region increases. And therefore, according to Lenz's law, the induced current and induced magnetic field will be opposite in direction to the original magnetic field, in order to oppose that change in magnetic flux. Once again, treating this induced magnetic field in the form of a tiny magnet, causing that induced field, you can see that the magnet would be oriented this way. In which case, you see here that the north pole of the falling magnet would be repelled slightly by the induced magnetic field, which we're treating as a small permanent magnet. So the fact that opposite poles, attract each other, on top we have a little bit of a retarding force coming from above the falling magnet. Likewise, we have an equivalent amount of retarding force, due to the fact that these like poles are repelling each other. The end result is that it slows, the falling magnet, because of this retarding force, that gets set up by the induced magnetic field.
I think you'll recognize this next demonstration of the ring launcher that I introduced in our lecture on current and resistance. For that lecture, I was interested in showing you that as the temperature of the ring was decreased, so was the resistance in it, which led to a greater current in it and thus a greater magnetic repulsion. What I did not talk about at that time was why the ring was launched in the first place. To do so would have required an understanding of electromagnetic induction and Lenz's law. And that's what we're going to be talking about in today's lecture. So here I'm going to demonstrate the ring launcher, which is a nice illustration of electromagnetic induction and Lenz's law. So here the ring launcher really just consists of this electromagnet. Right now there's no current in it, therefore there's no magnetic field. But once I push the button here, this will generate an alternating current in the ring launcher, the electromagnet. So I'm going to place this aluminum ring, on the ring launcher, and we can reason that right now there's no magnetic field in it, but once I activate the ring launcher, there will be a magnetic field in it. So the end result is that the magnetic field, penetrating this aluminum ring will increase in time. Now, according to what we know about Faraday's law and Lenz's law, this changing magnetic flux through the interior of the ring will then induce a current inside that ring. Now, according to Lenz's law, the induced current will create an induced magnetic field that is going to oppose the changing magnetic flux that created it. So because the magnetic flux through the ring increases in time, we can assume that the induced current and therefore induced magnetic field, must be opposite the direction of the original magnetic field, okay, in order to counteract the change in magnetic flux. Okay, because of that, that tells us that the field induced in the ring is going to oppose the original magnetic field of the electromagnet, causing magnetic repulsion. So as we would expect, when I activate this, okay, the magnetic repulsion is going to cause, okay, this ring to repel upwards. Okay, I'm going to do this one more time because take a look at the height of this, okay, rather thick, okay, aluminum ring. Let me put a thinner aluminum ring on there and let's see what happens. Okay, well, from what you know about our discussion of electrodynamics, we know that that thinner ring should have a greater resistance, okay, therefore will have less current when activated, therefore a smaller magnetic field will be created, thus less repulsion, okay, in which case you see that this ring doesn't go nearly as high. Okay. Very last thing we'll show, we'll use a split ring. Okay, and you'll notice here that for a split ring, okay, the results should not be surprising when I activate the electromagnet, okay, because there is no complete conducting path for that induced current. Therefore, there really is no induced current created, okay, no induced magnetic field, and therefore, okay, no magnetic repulsion.
So let's try to explain the launching of the ring, okay, in this demonstration. So you see here we have a ring which is sitting on this electromagnet, on this coil of wire. And it starts out with no magnetic field in the interior, but when we activate the switch on the ring launcher, okay, all of a sudden we have this intense magnetic field in the interior of our ring. This changing magnetic field from the alternating current powered coil clearly correlates with an increase in magnetic flux through the ring. Now remember, that ring you can think of as a complete circuit, as a complete conducting path along which charge can flow. So according to Lenz's law, okay, then this induced current, okay, produced by this increased magnetic flux, this changing magnetic flux, will create an induced magnetic field opposite in direction to the original magnetic field. Okay, that is because of the increase in magnetic flux through the ring's interior. So the induced magnetic field therefore opposes the original magnetic field in the coil, repelling it and pushing the ring upwards. Okay, as a follow-up, you'll notice that when we looked at the split ring, okay, a split ring cannot cause any induced current because there is no complete conducting path in which the current can exist. So for the case of the split ring, okay, it didn't get launched anywhere. And you also see that the higher resistance of the thinner ring causes a smaller current, okay, for a given induced EMF. Thus a smaller magnetic field will be induced, meaning less repulsion and ultimately less ring height. We are now going to look at a very important application of electromagnetic induction. This is sometimes referred to as back EMF, and see how this can lead to a condition often called motor overload. So if you think about any kind of appliance that makes use of an electric motor, when that motor is first turned on, okay, a large current surges through the coils in order to do enough work to accelerate the armature motor. Remember that that armature motor is starting out at rest and has a lot of inertia, so you need quite a bit of energy to be able to change its state of rotational motion. So as the armature begins to rotate, the moving armature coil in a magnetic field produces a changing magnetic flux through the coil, through the armature coil, which gives rise to an induced EMF. So as the picture on the bottom illustrates, once that armature coil is turning, okay, in a magnetic field, then we have a changing magnetic flux through that coil, and that changing magnetic flux should give rise to an induced EMF and induced current. According to Lenz's law, this induced EMF and induced current must oppose the change in flux that created it. This gives rise to an induced, sometimes called back EMF, that is opposite the source EMF, an induced current that is opposite the source current. So, as the motor speed increases, so does the back EMF, until it nearly balances the input voltage, meaning that the total potential difference across a circuit is small. Okay, according to Ohm's law, if the total potential difference is small, then so is the total net current in the circuit, and so is the frictional heating due to the I squared R power loss. So you can see what happens here, this condition referred to as motor overload, that when a mechanical load exists on a motor, okay, such that the motor speed decreases, okay, this causes the back EMF to decrease, and this means that the total voltage, okay, and total current in your device will increase. Okay, remember that your appliance is designed to have a certain amount of total or net current, okay, that is based on the armature turning at its operational speed. So if that armature is prevented from turning altogether, okay, there is no back EMF generated, okay, and large values of current will result, right? If your total current is only the source current and there is no back current, okay, produced by that moving armature coil, then you've got too much current for the design of the device, and it will quickly overheat. And this is the condition we refer to as motor overload. So many of you may have experienced this in life, whether you have a power tool that is prevented from moving, or the classic case is using a blender. Okay, if you're going to be making mixed drinks, that's why you always put the alcohol in first. Okay, if that blender, the blade is prevented from turning, that blender will very quickly overheat. So we are now going to take a look at a more quantitative example where we apply Lenz's law and Faraday's law. So in this example, this involves pulling a coil, a square coil, from a magnetic field. So we're told that a square coil of wire, okay, 5 centimeters on a side, containing 100 turns or 100 loops, is positioned perpendicular to a uniform 0.5 Tesla magnetic field. It is quickly and uniformly pulled from the field region, okay, moving in a direction perpendicular to the field itself, into a region where the magnetic field drops abruptly to zero. So right at the start of the problem, at time 0, you see here that the right edge of the coil is at the right edge of the field region. And it takes 0.1 seconds, a tenth of a second, for the entire coil to reach the field-free region. So in other words, in 1/10 of a second, okay, that coil will move a distance equal to its length, okay, so that the left-hand edge will now be in the field-free region. So we are first asked here to find the rate of change of flux through the coil. And you see here that as that coil is pulled to the right, okay, the flux through it changes in time. Certainly, once the entire coil is in the field-free region, there will be no change in magnetic flux, since, okay, any motion subsequent to that, there will be no magnetic field that penetrates it. But for the 1/10 of a second while the coil is being pulled from its initial position, okay, in the field region, okay, to its final position where the entire coil is now barely out of the field region, okay, for that amount of time, the flux through the coil will change as the amount of magnetic field penetrating it will change. So to figure out what the rate of change of flux is through the coil, let's start by getting an expression for magnetic flux. Okay, the surface integral of our field and this infinitesimal area vector dA. So you will notice here that when it comes to the cosine theta factor, okay, theta, that is the angle between the field and that vector dA, is 0 degrees. Notice that the field is directed into the plane of the paper, into your computer screen. Okay, the area vector by definition is perpendicular to the surface. Okay, so it too will be in the same direction as the magnetic field. Now, the fact that we can pull the magnetic field strength outside of the surface integral, there'll be a little bit more on that in a second, but it turns out that the magnetic field will be constant over the part of the surface that is in the field region. And therefore, our flux is simply going to be equal to the magnetic field strength times A, the area, but it is not the area of the loop, it is the area of the coil that is actually in the field region. So at any given instant in time, okay, that area of the coil in the field region will be given by this expression S times X. S being, let's say, the vertical length of the coil, and X, as you can see in the diagram I just put on the screen here, is really the amount of the horizontal portion of the coil, okay, the amount of that length that is actually in the field region. So the area we're really talking about is not the entire area of the coil. At any instant, it is simply the area of that coil that is in the field region. So given that expression for the area, we now have an expression for our magnetic flux, okay, being B times S times X. If we want to find the time rate of change of magnetic flux, that is the first derivative of the magnetic flux with respect to time, we will take the first derivative of it. And you will notice here in this expression BSX, okay, that the field B does not change in time. It's constant in time. S, the length of the side of the coil, doesn't change in time. So the only variable there that changes in time is this position X. So we will take the first derivative of X with respect to time. And when we do that, you will notice that dx dt is simply the speed with which the coil moves. Notice that that negative sign comes from the fact that X, that variable, is getting smaller in time, okay, as the coil is being pulled from the field region. So because it is decreasing in time, we put in that negative sign. So the last step then, finally, we got to plug in our numerical values here. We're going to plug in 0.5 Tesla for the magnetic field strength. The 5 centimeter coil length in SI units, we'll put in 0.05 meters. And the speed with which the coil is pulled from the region, okay, it is pulled a distance equal to its length, that is 5 centimeters or 0.05 meters, in a time of 0.1 seconds. So that really is the first derivative, okay, of X with respect to time. We do the number crunching and we get a value of 0.0125 Tesla meter squared per second, okay, for the time rate of change of magnetic flux.
We're next asked to find the induced EMF in the coil. Well, given what we found in the previous slide, that is the time rate of change of magnetic flux through the coil, then the induced EMF in the coil is simply given by Faraday's law, okay, by taking the opposite of the number of turns in the coil times that time rate of change of magnetic flux. So substituting the number 100 in for a 100-turn coil, using the result we derived on the previous slide for the time rate of change of magnetic flux, we come up with a value of 1.25 volts for the induced EMF. To find the current induced in the coil as a result of that EMF, given the fact that the coil resistance is 100 ohms, we simply use Ohm's law to find the magnitude of that current. So substituting in our induced EMF of 1.25 volts, the resistance of 100 ohms, we come up with an induced current, okay, to have a magnitude of 12.5 milliamps. Now, to determine the direction of that induced current, this is where we need to use Lenz's law. Okay, so we see that according to Lenz's law, as we pull that coil, okay, into the field-free region, we can see that the number of magnetic field lines penetrating it decreases in time. Okay, that is, the magnetic flux decreases in time, in which case the induced magnetic field will be in the same direction as the original magnetic field to oppose that flux change. And when we use our right-hand rule, placing the fingers of our right hand in the direction of, okay, that induced magnetic field, okay, we see that the thumb of our right hand will point in a clockwise direction around the loop. So the induced current for this problem, okay, will be clockwise.
In this next part of the problem, we're asked to find out how much energy is dissipated in the coil. So this energy really refers to the energy dissipated in the coil as heat, which is caused by this induced current. So anytime we have a current, even though the current here is quite small, there is resistance, and this frictional heating that is generated between these charge carriers moving down a conductor will produce a little bit of energy in the form of heat. So we can express that energy in the form of heat as a measure of the power generated in the coil times the time it takes for that coil to move through the field region. So this power, we're really talking about the I squared R power loss due to this frictional heating. So we'll multiply that by the time, the 1/10 of a second, to get an expression for the total energy dissipated during this process. And when we plug in our numbers here, it turns out we get about 1.6 millijoules, not a large amount of energy that will be dissipated in the coil as a result of that current in the coil, which is heating it up slightly. And lastly, we're asked to find the average force required to accomplish this move. So remember that anytime you have a current carrying wire in a magnetic field, that current carrying wire will experience a magnetic force given by this expression here. You'll notice here that the cross product here I put with this special notation here because we need to distinguish between the X in a cross product and the X, which represents the amount of the coil that is in the field region. So we're going to be using both in this problem, so I will use this symbol to represent the cross product. Now, this coil really consists of 4 sides, and there's really, in a way, 4 different forces that have different magnitudes and directions. So to find the total force on the coil, we need to break up this 4-sided coil into and take a look at each side separately. Starting with the top. From this expression, we find out that the force on the top portion of the coil has a magnitude given by N times the induced current times X, the amount of the coil in the field region, times the magnetic field strength, and that force is upwards. How do we get that? Let's take a look. This green arrow I'm showing you here shows you the direction of the induced current. We see the direction of the magnetic field goes into the plane of the paper, into your computer screen. So when we use the right-hand rule here for cross products, when we place the fingers of our right hand in the direction of the induced current, let them curl towards the second vector in the cross product, that is the field, right, IL cross B, you will see that your thumb is going to point in the direction of the cross product. And when you do that, you see that your thumb points in an upwards direction. If we look at the force that exists on the downward portion, the bottom portion of the wire, we see that it has exactly the same magnitude, right? N, the number of turns, times the induced current, times X, because the bottom portion of the wire, you still have only the amount X, which is in the field region, okay, that will be experiencing the force, times the magnetic field strength. To get the direction here, let's do the same thing we did above. Okay, this green arrow shows you the direction of the induced current. Okay, when you place the fingers of your right hand along the first vector in the cross product, let them curl into the plane of the paper towards the second vector, which is a magnetic field. You will see that your thumb points downwards. Notice that this upward force on the upward portion of the wire and this downward force on the bottom portion of the wire have the same magnitude, opposite directions, so they will exactly cancel out. There is no force on the right-hand portion of our wire loop. Why? Because that portion of our loop exists in a region without a magnetic field. So if there's no field, okay, there is no force on that portion. And lastly, when we look at the left-hand portion of the wire, we see that there is a force on that portion, a magnetic force, whose magnitude is given by N, okay, the number of turns, times the induced current, times S, that is the length of that piece of wire in the magnetic field, times B, the magnetic field strength. And we'll see that this force is to the left. So I'm showing you with the green arrow here, that's the direction of the induced current. Place the fingers of your right hand along that vector, okay, that's the vector L. In the direction of the induced current, let them curl inwards into the plane of the paper towards the second vector B, and you will see that the direction of that cross product, the direction of that force, is to the left. So, and when we plug in the numbers, it has a value of about 0.031 newtons. So this is the force that the loop, this is really the net force it would experience as it's being pulled, okay, from the field region to the field-free region. This is the force that the coil experiences due to that induced current. So that net force is 0.031 newtons to the left. The question really says, what is the average force required to accomplish the move? So they're really asking for the applied force in the problem. So you know from your study of mechanics that we would need to apply a force that is equal in magnitude but opposite in direction to that force, that magnetic force, in order to be able to pull that coil from the field region without causing any acceleration.
We'll now take a look at this concept of eddy currents as well as some of their applications. We'll start by distinguishing between induced currents in circuits versus induced currents in conductors in general. Thus far, our discussion of induced currents caused by changing magnetic flux has been limited to conducting wires, where currents flow in well-defined paths. But the truth is, any piece of conducting material that experiences a change in magnetic flux will experience an induced current. So when we talk about an eddy current, we're talking about a circulating current induced in a bulk piece of metal that happens to move through a magnetic field, okay, where the magnetic flux through that piece of metal changes in time. So here we have a nice way to demonstrate this phenomenon of eddy currents. And you'll notice here we have a pendulum here. Okay, and right now the pendulum is free to swing back and forth. Okay, you'll notice that in this region, when the pendulum is hanging down, we have these two solenoids here, which are going to produce a pretty intense magnetic field, okay, in the region when the pendulum, okay, the disc of the pendulum, okay, is in this position. And right now there's no current in the solenoid, so we have no magnetic field there. But let's take a look at what happens when we produce a magnetic field. I'm going to start the pendulum swinging with no magnetic field. I will quickly turn it on, and let's take a look at what happens to its motion.
Now you'll notice that for our pendulum, I've replaced the solid disc with a disc consisting of a bunch of slots. Okay, and you'll see that having the slots there, the effect it will have on allowing eddy currents to form. So let me let this rotate as we did before, and then I will turn on the magnetic field, okay, right now, and let's see what happens. Okay, you'll see there's a slight effect, okay, but the overall, okay, we cannot get eddy currents forming to the same degree, okay, when we break those, when we have a broken circuit, okay, with these slots. Let's now see how the formation of eddy currents can explain the retarding motion, okay, of the pendulum as it entered the magnetic field region. So when we apply Lenz's law here, okay, as always, we will start by identifying the change in magnetic flux. Now what we want to look at is we want to look at this region here as the pendulum is entering the magnetic field. You'll notice that as it enters the field region, okay, it experiences a change in magnetic flux, and it's pretty clear to see from the diagram here that this would correspond to an increase in magnetic flux as the pendulum enters the field region. So according to Lenz's law, okay, the direction of the induced current and induced magnetic field will be such as to oppose the change in flux. So because the magnetic flux increases, the direction of the induced magnetic field, okay, in that region will thus be opposite the direction of the original magnetic field. So if the original magnetic field is pointing into the plane of your computer screen, the induced magnetic field would be pointing out of the plane. And this induced magnetic field is caused by an induced current, which, using the right-hand rule, okay, would be in a counterclockwise direction. Now, this counterclockwise eddy current, when we look at its interaction with the original magnetic field, not the induced magnetic field, but the very strong original magnetic field, okay, we can think of that current in a magnetic field should give rise to a magnetic force. So when we look at the direction of that induced current in the region where the pendulum enters a field, it's in the direction I show you right here. Okay, and at this point here, we can bring back your buddy, okay, your right hand, and we can figure out the direction of that magnetic force, okay, caused by that induced current in the original magnetic field using our right-hand cross product rule. So remember, IL cross B, okay, is going to give you a force that is in this direction shown. Notice that that magnetic force resulting from the eddy current opposes the velocity, opposes the motion of the pendulum as it enters the field region. Okay, likewise, when we look at this region over here as the pendulum exits the field region, we see that that corresponds to a decrease in magnetic flux. And according to Lenz's law, the induced magnetic field must be in the same direction as the original magnetic field to oppose that flux change. This is going to give rise to a clockwise eddy current in that region. And if we look at the direction of that eddy current, okay, at the point where it exits the field, okay, that clockwise eddy current, then the direction will be here as shown. And once again, we have a current in a magnetic field, okay, in that original magnetic field, that is going to give rise to a magnetic force on the pendulum as it exits the field region. Using your right hand rule, okay, placing the fingers of your right hand in the direction of the induced current, letting them curl towards the second vector in the cross product, okay, the original magnetic field will produce a force in the direction shown. Once again, notice that the direction of that force is opposite to the direction of motion, okay, of the pendulum at that point. That force, that force opposes the velocity. So you can see here then the creation of this retarding force that happens because of the formation of the eddy currents. So in the eddy current pendulum demonstration that we just observed, we see that when a conductor is allowed to move in a region where a magnetic field exists, that the induced eddy currents interact with the magnetic field to exert a retarding force on the conductor. This phenomenon is widely used in technology. So for example, in braking systems for trucks and trains and even power tools, okay, we see how the formation of eddy currents can be used to slow down moving objects. Okay, rather than using friction between moving parts that will wear out materials like brake pads and brake drums, magnetic fields can be used that will produce no visible wear. So one more example to look at that we are all familiar with, okay, is that of the vending machine. And there's some really good physics here, okay, that we will take a look at. So the vending machine, okay, when you stick in your coin, it's really a two-stage security system, okay, for the machine to determine whether it's going to accept your coin or not. So when you stick the coin in the slot in this region here, the first thing that happens is that a potential difference is applied across the coin here in this position. And by using Ohm's law, okay, its resistance is measured. So that's the first, okay, security step in the process. Now, if the resistance is acceptable, the holder will then drop down and it will release the coin, okay, and allow it to roll along the inlet track here. And along this inlet track here, you see are these magnets. Okay, and these magnets will induce eddy currents in the coin, and the magnetic forces that will result will retard its motion and control its speed. So it turns out that the type of coin used, the material that the coin is made out of, will determine how big these eddy currents are and how big that retarding magnetic force is. So there are speed sensors here at the end of this track, and if the speed sensors indicate that the coin has an acceptable speed, okay, then you'll see here that gate B will swing open and allow the coin to be accepted. If the coin is not moving at the correct speed, okay, then gate C will okay, open down here and allow the coin to be rejected. So you see here how both Ohm's law and the retarding force that results from the formation of these eddy currents in a magnetic field, okay, can be used here to determine whether your coin is going to get you your candy bar. And finally in this lecture, we will take a look at a general form of Faraday's law. And if you're asking the question, what's the problem with Faraday's law as we've described it thus far, we see that there's a problem, okay, and this problem is illustrated nicely by Bongo here. So far in our discussion of electromagnetic induction, okay, it's been restricted to electric circuits. Faraday's law tells us that when you have a changing magnetic field and thus changing magnetic flux, that this will give rise to an induced EMF and thus induce currents. What would happen, however, if that changing magnetic field would exist in a region of space where there's no charge, okay, for that field to interact with? In other words, what if you have a region where there's a changing magnetic field and there is no wire, there is no circuit, there is no physical charge there? What happens in that case? Well, this is where we want to remember back to our discussion on electric current and resistance, where we ask the question, what is it that causes electric current on a microscopic level? And you recall that to explain the cause of electric current on a microscopic level, we would say that it's an electric field that causes current. So induced currents are caused by electric fields, and we can now say that it would be more fundamental to say that a changing magnetic field would create an electric field, such that if there was a circuit or charge present in that field region, then that electric field would exert a force on a charge carrier and give rise to an electric current. But if no charge happened to be present in that field region, and thus no current would be possible, we would still say that the electric field would exist in that region of space. So this is a more fundamental way of talking about Faraday's law. Rather than saying that a changing magnetic field in flux gives rise to an induced current, it would be more fundamental to say that a changing magnetic field in flux would give rise to an electric field. And that if there happened to be charge in that region, then we would get an induced current. But if there was no charge in that region of space, we would still get the creation of this induced electric field.
And finally, in today's lesson, we'll consider a generalized form of Faraday's law. So if you're naturally wondering, what is the problem with our description of Faraday's law thus far? Well, let's check out what our little buddy Bongo has to say about it. He kind of sums this up nicely here, and we'll take a closer look. So in our discussion of electromagnetic induction thus far, we have restricted our discussion to the case of electric circuits. Faraday's law tells us that if you have a changing magnetic field and thus changing magnetic flux through that circuit, it gives rise to an induced EMF, an induced current in the circuit. But the question is this: what happens when there is a changing magnetic field in a region of space, yet there is no charge that exists in that region of space for that field to interact with? What would you say in that case? Well, in order to answer that question, this is where we need to remember back to our discussion of electric current and resistance, when we asked the question many weeks ago, what causes electric current on a microscopic level? What is it that causes electric current in the first place on a microscopic level? Recall that we said on a microscopic level, we would say the fundamental cause of an electric current is an electric field that interacts with the charge carriers, thus exerting a force on them and causing them to move. So to sum this up here, we're saying that induced currents are caused by electric fields, in general. And it would therefore be more fundamental to say that a changing magnetic field creates an electric field such that, if there happens to be a charge present, then there would be a force acting on that charge carrier due to the electric field. And when a force acts on a charge causing it to accelerate, this is what we mean by an electric current. But what if there was a region of space where there was a changing magnetic field, which creates an electric field, yet there was no charge present and therefore no current possible? Well, what we're going to say is that that electric field would still be induced. It would still be produced, by that changing magnetic field and changing magnetic flux. So really what we're saying here is that, in summary, it would be much more fundamental to express Faraday's law by saying that in a region of space where there is a changing magnetic flux and field, that this changing flux and field would give rise to an induced electric field. And if there happened to be charge in that region for that electric field to interact with, okay, then that electric field would force the charge to move. We would end up with an electric current. But in the case where there was no physical circuit, no electric charge in that region, okay, we would still say that changing magnetic flux in that region would still produce an electric field, even if it could not interact with charge carriers to produce an electric current. That would be the more fundamental statement of Faraday's law.
In this slide, we'll discuss the difference between the electric fields that we talked about at the beginning of the course in our unit on electrostatics. That is, electric fields that are created by static electric charges versus the induced electric fields we're now talking about that get created by changing magnetic fields. So let's start with what we're familiar with. Okay, that is electric fields that are produced by static charges. And you recall when we talked about this concept of an electric field in our field line model, we said that electric fields have definite beginnings and endings. Electric fields start on positive charges and move away from positive charges, and these electric field lines will end on negative charges. So we can say that static charges produce electric fields that begin and end on the sources of the field, that is, on the charges themselves. Now, electric fields produced by static charges, okay, we said are conservative. You recall that when we defined this concept of electric potential, we did so by talking about the work that was done on a charged particle moving in an electric field. We said that the work done by that field on the charged particle as that particle moves from some initial position to some final position, that amount of work was independent of the path taken by that charged particle. And that's what made the force conservative. A way to quantitatively express this would be to say that the line integral, okay, that is F dot ds, okay, would have a value of 0 for the electrostatic force and the electric field, which are conservative. What we're now talking about in this unit, okay, these electric fields, these are induced electric fields that are caused by changing magnetic fields. And recall what we said. We said on a microscopic level, what is that would create an induced current in a circuit in a physical piece of wire? Well, we said it would be an electric field that would get created in that wire that would cause the charge carriers to move. When you look at an electric circuit, by definition, an electric circuit must form a closed continuous path so that when we have the magnetic flux in the interior of that circuit changing in time, that induced current must form a closed continuous path. We're now saying what would happen if you have the changing magnetic flux, but there is no physical wire there, okay, surrounding that region where the flux is changing. We're saying that on a fundamental level, even if there were no charge carriers there for the field to interact with to cause this induced current, the electric field itself would be created or induced. And in the same way that a circuit must form a closed continuous path, we say that an electric field must form, okay, a closed continuous path. In other words, an induced electric field must encircle the region of the changing magnetic field that creates it. Now, when I say encircle, you'll notice here in this diagram, I'm showing you circular electric field lines. Although in general, that electric field, it may not be constant and it may not actually be circular, but it will definitely, those electric field lines must form closed continuous paths, whether circular or not, around the region, okay, where the magnetic field is changing. These electric fields, these induced electric fields, okay, that encircle their sources are not conservative like the electric fields that are produced by static electric charges. And finally, we'll provide a statement of Faraday's law using this more general concept of an induced electric field as opposed to an induced current. So for circuits, Faraday's law took on the following form, telling us that when the magnetic flux through the interior of the circuit changes in time, an EMF and thus current are induced in the circuit. But we're now saying that even when no circuit exists in a region of space where the magnetic field changes in time, an electric field still gets created or induced. And that electric field forms a closed continuous path about the region of changing magnetic field. So let's see how Faraday's law would look quantitatively. On the left-hand side, okay, of Faraday's law, we see an expression for EMF that should look kind of familiar to us. The line integral, that is E dot ds, is how we defined electric potential difference way back in our unit on electrostatics. We didn't call it EMF back then, we simply called it electric potential difference. But you also notice that we didn't have that little circular symbol on our integral sign either. What's up with that? We're now saying that the electric field that gets created or induced must form a closed continuous path. Okay, closed continuous path about the region of changing magnetic field. And therefore, we must evaluate this line integral around a closed continuous path. Now, any closed continuous path should be valid, okay, but you recall that when you applied Ampere's law previously to evaluate the line integral involving the magnetic field, you wanted to choose a closed path, we called it an Amperian loop, that made the evaluation of the integral possible. Generally speaking, you chose a path where the direction of the magnetic field was known and where it was at least piecewise constant over the path. Okay, likewise, you will follow a similar procedure when evaluating the line integral involving electric fields. So for example, in this picture I'm showing you right here, okay, where we have this circular electric field created, okay, if I was to choose this green closed path, then you would need to know what does the electric field look like at any given point along that path, okay, and what is that infinitesimal displacement vector ds, what does that look like? Okay, you would need to know those two things in order to evaluate that line integral. So, do you really see that the left-hand side of Faraday's law, okay, this more general form, now looks really identical to that of Ampere's law if we were to simply substitute or replace electric field with magnetic field? Okay, so I'm just saying this because you have a lot of experience applying Ampere's law, and you'll notice here that with the exception of having an E for electric field rather than B for magnetic field, everything else about this expression and how you evaluate the line integral would remain the same. The right-hand side of Faraday's law, okay, involving our expression for magnetic flux, that side really doesn't change much from the way we expressed it for circuits. We're talking about evaluating a surface integral on the right-hand side as opposed to a line integral on the left-hand side, okay, where the surface is no longer, okay, the surface bounded by our circuit, but is rather the surface bounded by the closed loop we used in evaluating the line integral on the left-hand side. So this surface then Okay, the surface integral must be taken over any open surface that is bounded by the closed loop we use to evaluate the line integral, okay, on the left-hand side.